Welcome to this video on differences in differences estimation. What is the main idea of differences in differences estimation? Consider a situation in which you have two time periods and there are two groups. There's a group of individuals or units that have been treated and a group of individuals that have not been treated. However, treatment occurred in between the two periods or only for the second period. So that means in the first period, the treatment group is actually not treated and the control group is also not treated. And in the second period, the treatment group is treated, whereas the control group is not treated. Now, what's the main idea? So when we look at the control group and the evolution of the average outcome, then the difference in outcome over time measures time effects. So things that simply change over time that have nothing to do with the treatment. In contrast, when we look at the treatment group, the difference in the outcome over time is equal to this time effect, and in addition there will be a treatment effect. So we have the treatment group where we have a change over time that is the time effect plus the treatment effect, and we have a control group where the change over time is the time effect. If we take the difference between these two changes over time, so the difference between these two differences, then we will measure the treatment effect. What is the key assumption that we need to make for that? The key assumption is that the time trends for the baseline outcome are the same for treatment and control group. And this is called the parallel trends or common trends assumption. Now, we have talked elsewhere about random assignment, and this assumption here is an assumption on what we have called before why not I. The baseline outcome if no treatment occurs. So we make the thought experiment of not giving the treatment to those who actually received it in the second period in the treatment group. And then we would say, okay, what we want is that time trends in this why not are the same between those individuals who did get the treatment actually in our data and those who didn't. So under random assignment, we have the exact same things happening as we did for standard experiments, namely that under a random assignment, the why not will not be related to treatment assignment. So therefore, actually under random assignment, common trends will hold anyway. We will see that we can use data to see whether they do or are likely to hold even if there was no random assignment of treatment status, and this is actually one of the big advantages of this approach here, that we can use data where treatment assignment was not random. But we need to convince ourselves, and there's something that we can do about this, that we will talk about, that common trends actually do hold. It's easiest to remember all this in terms of a figure, I think. That's why I've drawn this up. So what we see here is on the horizontal axis time, we have two time periods. So that is the pre-period and this is the post-period. The dots are always average outcomes. And the solid dots are what we will have in our data. So we have two groups, we have two time periods. So we're going to have 1, 2, 3, 4 dots in our data. We have the evolution of the outcome in the control group. There's this one here. So in the first period, this is the average outcome. In the second period, this is the average outcome. There was no treatment for the control group. So this is a time effect for the control group. Think of things like wages. They simply change over time for everybody. It has nothing to do with any treatment that people receive. Now, what we can now take away from this control group is this evolution of the outcome, right? And we can use this when we think about what the data mean for the treatment group. So for the treatment group, we also have an outcome pre-treatment, and the first thing to notice here is that the outcome is not the same. So under random assignment, and this is actually one way in which we could test random assignment, what we would see is that the average outcome in the first period, where the treatment group actually did not yet receive the treatment, should be exactly the same as the average outcome for the control group, at least when we have enough data, many observations. Now we see here that it differs. And what this tells us already is that there is actually selection. So the difference between these two would be what we have before actually called selection bias. Here we don't have to worry about it so much because we have two time periods. So let's see how this goes. So this is the baseline outcome for the treatment group pre-treatment, and the treatment is only received in the second period. Now, if I take that time trend from the control group and I apply it to the treatment group, then I can construct a counterfactual outcome for the second time period. So this is what I'm going to predict the outcome will be. And then I'm going to see an actual outcome for the treatment group. And I know that the evolution from here to here, that will be a treatment effect plus a time effect. So when I only look at this with the time effect, I take this from the control group, then I get this. So the difference will be the treatment effect. So even though I have selection into the treatment, these two are not the same, I can measure the treatment effect as this difference here by constructing this counterfactual outcome, at least in terms of how I can imagine all this to work. In practice, what I'm going to do is I'm going to take this minus that, I'm going to take this minus that, and then I'm going to take the difference of these two things. Or even more conveniently, I can use OLS to estimate it. And the advantage is that then I will be able to do inference directly, because I'm going to get standard errors, and I can do a statistical test, right? And if I specify the regression equation in the right way, I can basically read off the output table what my treatment effect is, and I'm going to get confidence intervals and standard errors for that. So how do we do that? We define an indicator treated I for individual I if that individual is treated in the second time period. Then we define a next we define a dummy post T that takes on the value 1 for the second period. So what you see from this is that I'm going to have my observations indexed by I and T. So I stands for individual or unit I, and T stands for period. And period could be 1 and 2 or 0 and 1. So all you need is like a pre and a post period. And post will indicate that the data point is from the post period. The outcome for unit I in period T will be denoted by YIT. And then I'm going to have a vector of covariates as well. This is XIT. And with all this in hand, I can specify the following regression equation. The outcome is equal to a constant term alpha plus some impact of these covariates. We're not going to focus on that much, but I included them for completeness. Then the first interesting thing is gamma times treated. So what this will pick up is that the level of the outcome will be different between the treated and the control. So this is what I called a selection bias before. So in some sense we can directly estimate it here with this approach. Then I have a parameter gamma in front of the post dummy. So this will measure the time effect because post will be 1 in the second period. And this is the difference in the outcome for the second period, but actually for the control units, as we will see on the next slide in more detail. And then I have delta times an interaction term between that treatment dummy and the post dummy, and I have my error term. Okay, so I'm going to run this regression, and what I'll get is all these coefficient estimates, and it turns out that the interesting one is this delta here. The best way to see this is to go back to this figure. So what I've done here is I've again written down this equation here that we'll use to run our regression, and I now bring it together with this figure. So what we're interested in estimating is this difference here, and when you just look at this equation here, and you simply plug in treated is equal to 0. Then and you ignore for the moment the xit part. Then you see treated is equal to 0, so we're going to look at the control group, and post is equal to 0, so we're going to look at the pre-period. Then what we're going to get is alpha, and that's it, right? Because also this term here is going to be 0, and this is exactly this alpha here. So this data point here, is going to be alpha in terms of the average outcome. Now let's move to post. So I'm still keeping treatment equal to 0, treatment equal to 0. So also this term is going to be 0. So post, it's going to be alpha plus gamma, and this is exactly what you see here. So this is again alpha, and this here is, I'm sorry, that should be gamma. Let me just correct that. In fact, I apologize. It should be lambda. So again, I'm looking at the average outcome in the post period for the non-treated individuals. So treated is equal to 0. Post is equal to 1. And treated is equal to 0, so I'm going to have alpha plus lambda. Lambda is here, plus alpha, so it's all correct in this figure. So again, alpha plus lambda. And now let's look at the treated. Pre is going to be alpha plus now gamma plus plus gamma, no lambda, no delta, because post is still equal to 0, alpha plus gamma. And finally, the treated post are going to be alpha plus gamma plus lambda plus delta. So alpha plus gamma plus lambda plus delta. And yeah, what you see again is here, this is what we're ultimately interested in. So this is the coefficient on this interaction term here. That's going to be part of my OLS output, and it's going to come along with standard errors. Now, this all looks great. Of course, the issue is whether parallel trends or common trends are actually a realistic assumption, right? Whether we can do this thought experiment of saying that, we look at the evolution of the outcome for the control group, and this is going to tell us what would have happened to the treatment group had they not received the treatment. Of course, so far, I've looked at a somewhat minimalistic setup, so with 2 time periods. So when we have more time periods, what we can actually do is we can assess whether it's likely that this assumption holds in our situation. So in particular, what we can do is we can take data that are completely pre-treatment and redo the analysis and see whether we find an effect. Obviously, we shouldn't find an effect, so this is what we're going to test. The underlying idea here is that common trends or parallel trends is an assumption on the evolution of the baseline outcome, and pre-treatment, when I have more than one period, I will only observe baseline outcomes, so I can directly see whether the evolution is the same. So if the differences in differences estimator estimates a significant effect of this placebo treatment, then parallel trends will likely not hold. Conversely, sometimes it's highly suggestive when we look at the data that parallel trends is a good assumption. Again, in terms of a figure, what we now have is 2 more data points. So again, I have time here on the horizontal axis. I have the average outcome here, again plotted on the vertical axis. The data points I had before were these 4, 1, 2, 3, 4, and now I have 2 additional data points. Okay, and the way this now works is I'm going to use only data for these 2 time periods, which are both pre-treatment, because this vertical line is separating the pre-treatment period from the post-treatment period. So all these are pre-treatment. So what I should see in my data is what I've also plotted here in this figure, namely that the evolution of the outcome for the control group is the same as the evolution of the outcome for the treatment group. This brings me to a small, seemingly unimportant detail, but it's actually quite important in practice. You might remember that one can specify the outcome in levels or in logs, or in, or one can in principle use other transformations of the outcome. So it could be that in practice that parallel trends does not hold for levels, but it does hold for logs, right? So when I use a specification in logs, and this is something that I've explained in more detail in another video with the title Econometrics for Data Scientists, then this slope here, the slope in the figure, this will be a percentage change in the outcome. And it could be that the percentage change is the same in the control group as it is in the treatment group. And in that case, it would be a good idea to run everything in logs, and then parallel trends may likely be satisfied. Whereas when I plot this in levels, it could be that it actually looks very different. So this is just a little bit of an aside. Back to the core. So what I'm doing is I'm using these 4 data points here, and I'm using the exact same specification. The only thing is I'm specifying this placebo treatment. So I'm actually putting my post dummy equal to 1 for these 2 data points. Okay, and I'm doing as if this was a post period. So I'm discarding these 2 data points, and I'm doing as if this middle period was actually the post period. And I know it was not, so therefore I should find a 0 effect. It should look like this. If I do find an effect, then that is bad news, in the sense that it suggests that parallel trends may actually not hold. Now, this is not the end of the world. So in principle, one can allow for group-specific trends and dynamic effects. Let's think about this a little bit more. So let's broaden all this to more time periods. So when we start from the previous specification, what we can do is we can replace that constant term we had by 0 and add a fully flexible time trend for the control group. So these are going to be lambda t's in my model down here. And we can also include differential time effects delta t for the treated. So I can write it like this. Outcome is x beta plus gamma treated. So this will be the difference in the level, or what I called selection bias before. And again, selection bias is defined in the first video. Then I have these time effects, and I have the extra time effects for the treated group. Okay, and if parallel trends hold, then these delta t's, the extra time effects, will be 0 before the treatment is assigned. So it means the evolution of the outcome will be the same for the treatment and the control group. And after the assignment, delta t, actually, so in the post periods, now I'm using the plural, the delta t's will measure dynamic treatment effects. So how the impact of the treatment changes over time. Again, it's easiest to see this in a figure. Here I've again written down this equation. What you see here is again this vertical line. So these time periods are pre-treatment. These time periods are post. When they have the treatment, when they receive the treatment, you see the evolution of the outcome from here to here for the control group pre-treatment, and you see the evolution from here to here for the treatment group. So you see that this slope is not exactly the same as that slope, but they're similar, and this is reflected in this coefficient delta -1. So that would be then that would be capturing the differential time effect going from the last period pre-treatment to the second to last period pre-treatment. The difference in the time trend would be measured by this delta -1. Here, by the way, I've denoted this period here by 0. So you see here a 0 subscript. This is -1. This is -1, 0, 1, and 2. Good. So let's say for the moment that delta -1 is very close to 0, then it's meaningful to look at these. Then it's meaningful to say, okay, parallel trends or common trends holds approximately. And then what we can see is we can see that the evolution of the outcome for the control group is like this. It goes down and then up again. And this is captured by the change from lambda 0 to lambda 1 to lambda 2. And the evolution for the outcome for the treatment group is actually going from lambda 0 plus gamma to lambda 1 plus gamma plus delta 1 to lambda 2 plus gamma plus delta 2. Okay, so again, gamma as before, that's our level difference in the outcome between the treatment and the control group. This is what we called selection bias before. So here we just estimate how big it is, so we don't have to worry about it actually. So what stays then is this delta 1 and the delta 2. And delta 1 and delta 2 now tells us what the effect of the treatment is in the first period in which it was assigned and in the second period. So we see that actually delta 1 is slightly bigger than delta 2, so that means that the effect is bigger in the first period after assignment. Some details. So here again, this is the equation that I had on the previous slides. So as I said, we have specified that t is equal to 1 in the first period with the treatment, and we have set delta t equal to 0 in the I'm sorry, I've just corrected that. We have set delta not equal to 0. So delta not is the difference in the time effect between the treatment and control group. So that is our baseline. Let me briefly go back one slide. So here we had a delta minus 1, and here we have imposed that delta naught is equal to 0. Okay, gamma naught, lambda naught is the time effect for the control group, and all the difference in the level is captured already by this parameter gamma. So it's actually okay to set one of the deltas to 0, and what we have chosen to do here is to set delta not equal to 0. Okay, so and this is taking a stance. So it's saying that our baseline period is the last period before the treatment was received. So everything is measured. Also, the treatment effect is measured relative to that last period pre-treatment. Alternatively, what one could do is one could say that one imposes that all the deltas pre-treatment are 0 on average. So that would mean that one would say, hey, my baseline is not the last period pre-treatment, but it is the average period pre-treatment in terms of the differential time effect, which is denoted by delta t here in this specification. It will slightly change the results because, as you can see, it will move this this dashed line a little bit up if I impose that these two are 0 on average, and then it will make those two deltas slightly smaller, but normally it doesn't make a big difference. And normally it's actually the most natural thing to say that the last period pre-treatment is the baseline. Good. So you might now wonder, okay, this sounds great. How can we implement this in practice before I run OLS, and what do I need to do now? It's actually very easy. So what you need to do is you run OLS as before, and the specification you use is one without a constant term, with a full set of time dummies. So these are gonna then have the coefficients lambda t, a dummy for the treated group. That's gonna estimate, gonna have the coefficient gamma. A full set of time dummies interacted with the dummy for the treated group. So this will be then capturing or giving us the estimates of delta t. And what we have to do is we have to leave out the interaction term between the time dummy and the treated group for period 0, which is the last period pre-treatment. How can I test whether parallel trends is likely to hold, or how can I do a test that supports this assumption of common trends? Well, I'm gonna test here whether delta minus 1, and that will be the deviation from the parallel trends pre-treatment, is different from 0. And hopefully it's not, which then gives more credibility, or gives credibility to your analysis. If parallel trends hold, then as I said, delta 1 is the effect of the treatment in the first period, and delta 2 is the effect of the treatment in the second period, and that is sometimes called a dynamic treatment effect framework, because we allow for the evolution actually of the treatment effect over time. let's quickly think about things that could go wrong. So what could go wrong is that you have a treatment group and a control group, and the composition of these groups changes over time. Such changes could come about for various reasons. They could also be related to the treatment. So, for instance, after doubling education spending on public schools, rich parents might take children out of private schools, right? If the treatment is public school, right? So over time, you could see actually such changes in your data. If they occur and you don't control for them, then this might be a source of bias. So therefore, it's a good idea to check whether the composition of the treatment and the control group is stable over time. And if it's not, one could check whether the changes are at least comparable across groups. And to some extent, one can remedy all these concerns by controlling for group composition. And this was actually the motivation for having this variable xi t in our model, right? So that could actually capture compositional changes, and if you include enough information in terms of an xit, it might be fine anyway. So if you are worried that, for instance, the treatment group is increasingly high-income people, and you control for income, then it might be fine that common trends actually hold once you control for income, but they don't hold when you don't include income into your XIT. Let's look at a little bit of an example. This is a classic example, and this is just meant to illustrate actually what can go wrong. This is a classical study by Card and Krüger, published in the AR in '94. What they looked at was an increase in the state minimum wage. And this happened in New Jersey. In neighboring Pennsylvania, the minimum wage stayed the same. They collected data on fast food restaurants in both states, and then they looked at employment. Okay, and the idea is that maybe when the minimum wage is raised, it leads to negative employment effects, but it could also lead to positive employment effects for all kinds of reasons that are more complicated. Something like people have more money in their pockets, they go more to these restaurants in the first place, so this gives them good business, and therefore, in the end of the day, more people work. So stories like that could be at play, and their aim was to look into that in this setting. So what they did was to compare employment changes in New Jersey between February and November with employment changes in Pennsylvania in the same period. And I'm already putting here two things that could go wrong. So in some sense, they really have like 4 data points. And this was the starting point of this presentation here. So there could be different trends, and there could be compositional changes. And when you look at this figure here, and this is from a follow-up study in 2000, where they looked at more data, basically, all this becomes quite clear. So what we see here is a solid line. This is the evolution of employment in New Jersey. So again, New Jersey was the state where the minimum wage was increased. So this is the pre-period, this is the post-period, and they conducted their study basically using 2 data points here and 2 data points here. And what we see in this figure here is actually data at a higher frequency that they collected later. Okay, and when you normalize things so that employment in the first period is equal to 1, so you measure everything relative to that, then what you see is actually that employment increased in New Jersey, where the minimum wage was increased, whereas in Pennsylvania, it actually decreased slightly. So what they find is basically a positive effect, effect in quotes, of raising the minimum wage. But when you look at the bigger picture, and this is what they did later, then it seems that they're really comparing apples to oranges, in the sense that the time trends are very different, right? So what you see in New Jersey is basically much more flat. There's much more dynamic in Pennsylvania, and also in Pennsylvania, they initially calculated data from 7 counties. So this is what you have here, this line here. When they broaden this and calculate data from 14 counties, the evolution looks again different, right? So in some sense, what this shows is that things are really not robust. So we shouldn't trust their original results too much. If anything, it looks like there was not much of an effect, at least before some other change, which was some extra increase in the minimum wage that was nationwide. But I don't want to talk about this in this video here in more detail. What you should take away from this is that when we look at it again later with much more data, it puts all this into perspective, and what we can see is that we should really take it seriously to make sure we are convinced that common trends is actually a good assumption, which here it doesn't seem to be. Good. A generalization to all this is the so-called synthetic control approach or method. What's the idea here? So let's say parallel trends don't hold. Okay, so you see directly in lots of pre-treatment data that this doesn't really hold. Still, what you can do then is to construct a synthetic, an artificial control group, simply as a linear combination of potential or of potential control groups, right? This was initially suggested by Abadi with co-authors in a paper in JASA in 2010, and this is implemented in many software packages, so you can just download this. And you can run it yourselves. Of course, one still needs to make sure that one can convince oneself, and hopefully also the audience of one's study, that there are common trends or parallel trends between the treatment group and the synthetic control group. So how does that look? This again from their paper, actually. So what they did was they looked at the effect of Proposition 99 in California. There was a large increase in tobacco taxes and earmarking tax revenues to fund anti-smoking measures. So what should be the case is that cigarette sales should be negatively affected by that. Okay, so when you look at the raw data and you compare California to the rest of the US, then that comparison doesn't make much sense, you see already, because this dashed line here, or dotted line, is dashed line. This dashed line gives us the time at which this became effective, but you see that the pre-trends are very different between California, which is solid here, and the average state in the rest of the US. Now, what you can do is you can basically form a different linear combination of states. You take a different weighted average of what is happening in states, and you can do that so that actually the pre-trends are matched, right? What you need to convince yourselves is that this all makes sense and that they're matched well enough. But here in this figure, you see that they do a great job, so it seems to work. And then the idea is that you look at the evolution of cigarette sales for these these other states combined, like in this other way, the synthetic other state, and you take this as a baseline, and you look at the evolution of sales in California, and the difference is going to be the effect. So here you see this directly. So in a way, what you have here is you plot the effect over time, and this is what we called before a dynamic treatment effect. So these are the delta t's that are basically plotted in this last figure here on the right. So these are the delta t's post-treatment, and here are the delta t's pre-treatment. And here you see actually what I said before, that basically they impose that the delta t's pre-treatment are equal to 0. Instead of imposing that the last delta t is equal to 0. But here from this figure, you also see that it doesn't make much of a difference in terms of the interpretation of the results and the general takeaway. What else is happening? Well, there are new promising developments, and this has to do with machine learning and data science, after all. So the question, why not use big data to construct a counterfactual nonlinearly? After all, big data is good for making predictions, and we have all kinds of methods that are good for that, are constructed for that. This is advocated in a recent, well, not so recent anymore, in a paper by Halvarian. I've put the reference here. It's a nice read, so I can warmly recommend reading that. It's a light read. It gives you a bit of a bigger perspective on what is happening and how this could be useful. And what he says is that, for instance, one could use data from Google Trends for this, right? To make predictions, and you use only the pre-period to sort of train the model, and then you use this in a similar way as we did see for the synthetic controls to predict what would have happened to the treated units had they not received the treatment. How does this look? So what we have here is website visits as the outcome. You have the US clicks, that is the solid line here in the pre-period. Okay. You have the model fit, that would be the blue line. So you're very good at fitting the data. Yeah, so this works very well. So this is the pre-period. Then we have the treatment period. So this would be this period here. So in the treatment period, you can, use the model to make a prediction. There's this dashed line here, and you can compare the actual evolution in solid line to the prediction. Here, it's just the difference that is plotted. And then here, this is actually a period in which the treatment stopped, right? So what should happen then is that the actual website visits go back to the prediction. And the cool thing is they do, in the sense that the effect, the difference between the two actually goes to 0. So this works quite well. And arguably, this is quite convincing, what they show here. So, to conclude, what are the key concepts? The key concepts are, how it all works, of course, and it's all based on common trends, parallel trends. This is an assumption that you can provide supportive evidence for if you have more time periods. We have seen how this works. In the end of the day, differences in differences estimation is comparing the evolution of the outcome between treated and control units, and these control units, as we have seen, can be also synthetic controls, and it can also be a prediction based on big data. In the end, we have something that is called fixed effects. In the end of the day, this is fixed effects estimation, what we're doing here. We're looking at the evolution over time, and we basically by doing so we we control for level differences. So the selection effect that we talked about is in the model. So we estimate how big the selection effect is, and that then allows us to learn about the treatment effect without random assignment. And the last thing I put here is the synthetic control method, because in the end of the day, this is one of the generalizations that is probably most promising as a development here. Good. So this is a very powerful method that we've gotten to know here. I hope you found this presentation helpful, and with this, all the best.